Alright, we have now completed 3 of the 7 sections and we will now do section 4, which is linear functions. So what are linear functions? Well, let's think of this linear equation in 2 variables, x minus y equal to 1, which has this graph, this straight line plotted over here. And let's write the variable y in terms of the variable x. So we have x minus y equal to 1. I want you to isolate y and write it in terms of x, and then we will make the connection to functions. So x minus y is equal to 1. Let's isolate y and let's add y on both sides. So I get x is equal to y plus 1. Now subtract 1 on both sides, so I get x minus 1 is equal to y. So y in terms of x can be written as y is equal to x minus 1. And as you can note, this is the slope-intercept form of the lines equations, y equal to x minus 1. Now here's the thing, if you think of this equation as expressing y in terms of x, you can think about y being a function of x. So if x is your independent variable plotted on the horizontal axis, y is your dependent variable plotted on the vertical axis. So y is in a sense a function of x, and the definition of that function is x minus 1. So we can think of y, the variable y, as a function of x, and the definition of that function is x minus 1. And this is a linear function because we got to this from the equation of a line. So that is the connection between lines, linear equations in 2 variables, and linear functions. Very, very straightforward. But now let's get into this a little bit more deeply. So now we'll talk about the rate of change of a linear function. So here's the graph of a linear function. F of x is 2x plus 1. This is actually equivalent to the linear equation y is equal to 2x plus 1. And the slope of this line, as you know, will be 2 and the y-intercept will be 1 because this is the slope-intercept form. We know how to read it. This coefficient is the slope, this constant term is the y-intercept. But let's also now analyze this in terms of the rate of change of a function. So what is the rate of change of a function? So the rate of change is the ratio of the change in the function's value, so delta f of x, by the change in the variable's value. So delta f of x by delta x. So if we take, let's say, 2 values of the variable, so let's take x as negative 1 and let's take x as 1. So for x equal to negative 1, f of x will be, or let me write this as f of negative 1. We can see it from this graph here. So for x equal to minus 1, f of minus 1, negative 1 will be negative 1. And for x equal to 1, f of 1 will be, let's see, f of 1 will be 3. Alright. So the change in the function's value is 3 minus negative 1, which is 4. So delta fx is 4. And the change in the variable's value is 1 minus negative 1, which is 2. So we get the rate of change as 4 over 2 or 2. And this value is the same as the slope of the line. And this is no coincidence really, because in this case, we are dealing with a linear function and the rate of change of that linear function is identical or equivalent to the slope of the line, because what you're really calculating here is simply the change in the function's value, which is the rise, over the change in the variable's value, which is the run. So this over this is what you're really calculating, and you get it as 2, the slope of the line. And this also tells you that the rate of change of a linear function will be constant because the slope of a line is constant. So that's the key takeaway from this slide. The slope of a 2-variable linear equation and the rate of change of the corresponding linear function, they are essentially equivalent and they are constant. Now here's a very simple SAT sampler on linear functions. So we have this linear function f of x is 5x plus c. So once again, this is equivalent to the 2-variable linear equation y equal to 5x plus c, the line y is equal to 5x plus c. But actually this problem is quite straightforward. it says if c is a constant and f of 3 is 17, what is the value of c? So it's a simple substitution problem. Instead of x, we plug in 3. So we know that f of 3 is 17. So f of 3 is 17. But f of 3 should also be 5 times 3 plus c. So 17 should be equal to 5 times 3 plus c. So 17 should be equal to 15 plus c. And you subtract 15 on both sides now. And this means that c should be equal to 2. So c equal to is the answer to this problem. Now here's our next SAT sampler. The table shows some values of x and y with a linear relationship between them given by y equal to ax plus b. So this really tells us that y is a linear function of x. And if you want, you can also interpret this as the equation of a line in slope-intercept form. We have to find a and b, and we are given these pairs of values of x and y. Now, our job is made easier by the fact that we are given this pair 0, 7 for x equal to 0, y is equal to 7, because if you substitute x equal to 0 here, you get y equal to b, and we know that that value is 7. So from the table, we can immediately infer that b should be equal to 7. Now, how do we find this value a? Now, this, remember, is the rate of change of the linear function or the slope of the corresponding line. So we can take any two pairs of values and find the change in the function's value, delta f of x, and divide it by the change in the variable's value, which is delta x, which once again, if you want to think in terms of lines, you can think of this as rise over run. It's the same thing really. So let's take these two pairs of values. So the change in the function's value is 11 minus 7, that's 4, and the change in the corresponding change in the variable's value is 2 minus 0, that's 2. So 4 over 2, that is equal to 2. So the rate of change of this linear function is 2, or the slope of the corresponding line is 2. So a will be equal to 2, and that's so therefore the function is 2x plus 7. All right, so that completes the problem. A is equal to 2, b is equal to 7. Now here's a challenge for you. Imagine that in this table of values given to you, this entry was omitted. It was not provided. How would you have found a and b in this case? Try this out on your own. All right, now here's the next theme in this section: modeling real world situations using linear functions. And here is an SAT sampler problem in this theme. A phone company offers a monthly plan where the total cost in dollars is given by the function c of n. C is the total cost, so c of n is 25 plus 10n, where n is the number of gigabytes of data used. What does the number 10 represent in this context? What does this 10 mean? Well, to help you understand this, let me just make the situation a little more concrete for you by taking some actual values for n. So let's say n was 0, which means that the number of gigabytes of data used was 0. In that case, the total cost would be c of 0 would be 25 plus 0 or 25. Okay, great. If n was 1, which means 1 gigabyte of data was used, then the cost would be c of 1, which would be 25 plus 10 or 35. Let's take one more value, n equal to 2. In this case, the cost would be c of 2, which would be 25 plus 20 or 45. So what do you think is happening here? So if even if no data was used, this case, we would still get a cost value of 25, which means 25 seems to be the fixed cost associated with this monthly plan that would appear regardless of the number of gigabytes of data used. And then for every additional gigabyte of data used, the cost is increasing by $10. So we're going from 25 to 35, 35 to 45, and so on. So in this case, 10 is really the rate of change of this function. Or if you were to plot this as a line in a plane on the graph, you would get the slope of the line as 10. And from here, it's evident that the meaning of this 10 is the cost per gigabyte of data in dollars, because for every additional gigabyte, the cost is increasing by 10. So 10 is the rate of change or the slope, and in this context it means the cost per gigabyte of data in dollars. So C is the correct answer. Now here's our next problem. In 2015 there were 100,000 electric cars registered in a certain country. The number of electric cars is estimated to increase by 25,000 each year. So we are starting with 100,000 in this year 2015, and then every year there is an increase of 25,000. Which of the following equations models the estimated number of electric cars E t years after 2015? So again, this is a really straightforward problem on linear functions. So the initial value in 2015 is 100,000 electric cars. So 100,000, let's write it. And then every year the number of cars is increasing by 25,000, which means 25,000 is the rate of change per year. So after t years, the increase would be 25,000 times t. So we'll just add to this initial value, we will add 25,000 t, and this will give us the total number of electric cars, or E, after t years from 2015. So as you can see, this is a linear function. E, the variable E is a linear function of t, and this 25,000 here really represents the rate of change, the increase per year in the number of cars, and 100,000 is our initial value. So that's how you would do this problem. So which option is correct? 100,000 plus 25,000 t. So option A is the correct answer.